Hello, and welcome to Lattice Gauge Theory for High Energy Physics, Module 10. The topic today is lattice QCD for spectroscopy, resonances, and nuclei. And I'm Professor Will Detmold from MIT, and I'll be the lecturer for this section. So let's start with a motivation as to why we might be interested in spectroscopy. Spectroscopy is really a key part of learning about QCD and the non-perturbative regime. The spectrum of the theory is really the simplest quantity you might ask about. And one question we can ask is, does QCD describe nature? So for many years, since the 1970s, we've really known that QCD can be confronted against high energy experiment at colliders and is seen to describe what we see in experiment. And the way in which we test this is by doing perturbative calculations in QCD and seeing that they describe what goes on. But really, from these experiments, we do not test whether QCD is actually describing nature as a whole, really just the high energy regime. And an interesting question is whether it also describes low energy properties such as the QCD spectrum. And it's really only since around 2010 that we've had lattice QCD calculations of the spectrum that really tell us that even in the strongly interacting regime of QCD, it does agree with the experiment. And 2010 is really the year in which the first completely controlled calculations for spectrum came out. So let's start with a couple of questions for you. So one is, how is the proton mass a test of QCD? So you may have heard that, or you may know that QCD calculations contain some parameters, the quark masses and various other things. And maybe you can tune those parameters to agree with any proton mass. And a good question to think about is, what ways can we tune those parameters? What are some of the ways? And if you've tuned those parameters, can you test? Can you use the proton mass as a test for QCD? Okay, another question, related question. So the proton mass is very precisely known from experiment. And a good question for you to check is how many digits? So can this quantity be used as a test of the standard model? Okay. Um, Moving on, a motivation for spectroscopy is really provided by contrasting QCD against the quark model. So the simple quark model that was written down in the 1960s and its evolution into more dynamical models such as MIT bag model and soliton models, these provide somewhat compelling pictures of what's really going on in QCD. And they're able to reproduce the basic features such as the low energy spectrum at roughly the 10% level. And things like large NC expansion and holographic models. But one question you've got to ask is, are these pictures that these models provide based on anything more than like an intuitive view of what's driving confinement of quarks inside the hadron? And do they make predictions? And the answer is yes. They, in fact, predict a whole host of excited states of hadrons. And this is something that we can test in an experiment and through lattice QCD calculations. So the quark model also predicts there are so-called exotic channels in which there are no states you can make from simple like quark antiquark mesons or three quark baryons. And these exotic states are something that is natural to search for in experiment. And by looking in these channels in particular, you can really see that QCD is more than the quark model. Um, so another motivation for looking at spectroscopy is that experimentally hadron spectroscopy has been undergoing a renaissance over the last decade. And so we're learning lots of new things, of lots of new features of spectroscopy that for the first time that really uh, we can try and confront against lattice QCD calculations. And there are many new qualitatively different phenomena that have been observed for the first time. So a lot of this is driven by the LHCb experiment, but also the Best 3 experiment in China, the Bell 2 experiment, and others. And in fact, the second, uh, um, so if you look at the papers that have come out of the LHC, there are really 4 papers related to the Higgs boson, and then the fifth most highly cited paper of the LHC is the LHCb's observation of a pentaquark state. And as well as pentaquarks, which are obviously not the simple constituents of the quark model, so quark antiquarks or 3-quark baryons, um, these experiments see tetraquarks, um, such as the TCC++, um, also doubly charged, doubly heavy baryons, um, and also a lot of new states that just defy the quark model expectations. And so a natural thing we can try and do with lattice QCD is compute the Hadron spectrum and confront these experiments. So let's start quickly with a little bit of nomenclature. So firstly, we can talk about stable particles. And a question is, what are all of the stable particles? So try and make a list of those. And maybe another question before we do that is, how many new states has LHCb discovered? Okay, so these particles that are stable under all of the interactions in nature are something that's obviously very important. From the QCD point of view, we can ask about so-called strongly stable particles. And so these are particles that are stable if in pure QCD. But for example, they may decay through electromagnetic or weak interactions. And so, for example, things like the pion, which under QCD is a perfectly stable object, would, of course, decay weakly. So just some examples. Yeah, we've got the pions, the kaons, the proton, the neutron, lambda, um, uh, the sigma b, and so on. And this is actually an interesting fact. This classification depends on the quark mass. So in nature, the rho meson or the delta baryon are unstable particles and decay via the strong interaction. But if you change the quark masses, you can go to a regime where these are stable. Okay. Um, we can also talk about resonances. And resonances are unstable under the strong interaction. That appear as enhancements in scattering cross sections experimentally. And yeah, as I mentioned, we also can talk about exotic hadrons. These are the states that with quantum numbers that are not allowed in the quark model, as Q bar Q or QQQ objects. Okay. So we can also talk about more complicated objects, and we know these very well. For example, in particular, we can talk about nuclei. And so from the QCD point of view, nuclei are really just another tower of hadrons. Just some other more complicated, messy combinations of quarks and gluons. And really what uh, makes them different than the proton and neutron and the mesons we've talked about before is that they have a conserved baryon number that's greater than 1. And of course, you know, there are many different nuclei. There's the stable nuclei, and then there are, of course, unstable nuclei with different proton and neutron numbers. And there's a whole enormously rich phenomenology of nuclear physics that comes about from them. However, if you think about it from the standard model point of view, again, almost everything that we know about them is determined by 5 parameters. So there's the fine structure constant, electromagnetism. There's the strong interaction coupling. There's the mass of the electron, mass of the up quark, and mass of the down quark. And in almost all pieces of phenomenology, these are really the only things that that matter for nuclei. Okay, so let's think about QCD again. And here's another question to dwell on. So if you're given the QCD Lagrangian, um, what I want to ask is, can you tell me which of the following pictures is a more accurate depiction of say helium-4. So let's think about four different pictures. So let just for contrast for my drawing, let's say this is the proton. And so he's got a, oops, it's got a blue quark, a green quark, and a red quark. Okay, so now let's try and think about helium-4. So, okay, so for A, let's think about this thing here. Actually, let me redraw that. B, and you can add gluons to these pictures, of course, but I can't do those. Okay, what about and finally, oops, very good. Try and draw that again. Okay, so that's something to think about. Now, let me give you a exercise to work on. So simple question. So what is the mass of carbon-12 in MeV? And how does this compare to its constituent nucleons? So it has 6 protons, 6 neutrons, and 6 electrons. And also, how does this compare to its constituent quarks? And so the 6 protons have in the quark model have 12 up quarks, and the 6 neutrons have 6. So we have 18 up quarks plus 18 down quarks plus 6 electrons. So just think about what the different masses occurring in each of these are. And you'll find an interesting thing, and that is that the mass of carbon-12 is within 1% of the mass of the 6 protons, 6 neutrons, and 6 electrons. And a question is, from the Q-steady Lagrangian, which is really saying that the binding energy of nuclei is small compared to the rest mass of the constituent nucleons. And in fact, I think this question is probably one of the most interesting things you can ask about nuclear physics. And it's really another way of phrasing this is really asking, why is the smallest baryon number color singlet, the proton or the neutron, such an effective degree of freedom throughout all of nuclear physics, or all of strongly interacting matter? In all of the nuclei we see, it provides a very good description at some level, and even in objects such as neutron stars. Okay, so let's be a little bit more practical. So there are also many reasons why many phenomenological reasons why we want to understand the physics of nuclei from the Standard Model. Um, Let me not dwell too much on this, but uh, nuclei are used as targets in many experiments. So, for example, at the intensity frontier, so for example, looking for dark matter in lab experiments um, or looking for neutrino nucleus interactions at Dune. Um, And so in these experiments, we really use nuclei as targets because we need to assemble a large number of them because of the very small cross sections. And so although I think perhaps it would be nicer to just use protons as targets, we really can't make a dense enough medium just of protons. Okay. Also, nuclei allow us to test important aspects of symmetries. And symmetry breaking. And just as two examples, we have deformed nuclei which break spatial symmetry and also have very high electric fields within them, provide a perfect location for searches for time reversal violation through electric dipole moments, for example. Um, and also nuclei can undergo neutrinoless double beta decay, which would allow us to, and searching for that allows us to test whether barrier number minus lepton number is a good symmetry. Um, okay. So some nuclei have properties that it's not possible for a proton to have. And this is really because nuclei are allowed to have many different quantum numbers that are not accessible to a proton. So one example of this is nuclear gluonometry. And I won't tell you what this is. I'd ask you to go and have a look. But it's really a property that a nucleus can possess that a proton and neutron do not. All right. So there are also many fine tunings in nuclear physics. And I alluded to one of them, which is why binding energies are very small fractions of the rest mass. But there are many others. Um, and really, I suppose the best example is the triple alpha process, through which carbon forms in the universe. And this occurs because there's very close degeneracies between energy levels in um, scattering of an alpha particle on a beryllium resonance. And if the energy levels move around a little bit, the amount of carbon that gets produced would either be very large, very much more than we have in the universe, or very much less, and we may not be here. Um, and it's an interesting question is how these depend on the quark masses, on the parameters of QCD. And this is only a question you can answer with lattice QCD. And finally, as motivation, um, nucleon interactions, and more generally, uh, hyperon nucleon interactions, and yeah, hyperons are things like the lambda baryon, the sigma baryon, and the cascade baryon that contain strange quarks. So these interactions between these different particles are very important for understanding the structure and dynamics of neutron stars. And with the LIGO's observation of neutron star mergers, this is really a very active field of research. Okay, so that is the motivation. Let me add a couple of slides here. So let's talk about how we do lattice QCD spectroscopy. Okay, and of course the spectroscopy is defined by the eigenstates of the Hamiltonian. And in lattice QCD, we always work in a finite volume. So unlike in nature, where the spectrum of eigenstates becomes continuous, in a finite volume, we always get discrete energy eigenvalues. In lattice calculations that actually connect to experiment at the moment, these are all performed through the path integral language. And so we don't have direct access to the Hamiltonian. And I'm really contrasting this to uh, the discussion of doing QCD on quantum computers that we had last semester. But that's really limited at the moment to toy models, and so is not directly confronting experiment. And so the Hamiltonian isn't directly accessible. However, given certain conditions, and we won't go into these in any detail, um, but they're called the Osterwalder-Schrader axioms. Um, a Euclidean action is guaranteed to give rise to a Hermitian Hamiltonian and a well-defined Hilbert space. Um, yeah, so a and so it does make sense to ask about the spectrum of this Euclidean theory and connect it to the spectrum in Minkowski space. Um, so let's go ahead, and so we take our the eigenstates of our Hamiltonian, and so these are a set of states in and because the Hamiltonian is Hermitian, we can resolve the identity in terms of these states. Okay, so given the Hamiltonian, we can look at correlation functions of the theory. And in fact, the time dependence of correlation functions is going to give us access to the spectrum. So let's define a correlation function, and I'll call it C2 of T and P. And I'm going to be fairly explicit here, just go through everything in careful detail. So first, let's write it in terms of the path integral. I won't specify which fields we are talking about, but you can think about this as being QCD. So it's path integral weighted by the Euclidean action And then I'm going to define this to be x, and it's a correlation function built from two operators, chi, which is a function of the fields, x and t, so a local composite operator, and chi twiddle is a function of the field somewhere else at x0, t0. And I've put the subscript q um, on these fields to define some set of quantum numbers. And we'll come back exactly to what these chi's are later on. Okay, so let's write this now in terms of the language of operators. So alternatively, this can be written as a trace over h t as in, I guess, right here, a cubed sum over e to the minus I p dot x. I guess there's an a cubed here too. And so this is the sum over sites in my lattice. Actually, let's do that a bit bigger. And then we have the operator definition, chi q of x t, and then chi twiddle dagger. And I believe this is x naught t naught. And this is divided by the partition function, which is just the trace of e to the minus ht. And of course, the path integral on the first line, in order to have an interpretation in terms of a statistical system at finite temperature, the fields are required to satisfy boundary conditions, and t is the temporal extent. Capital T is the temporal extent. Let me indicate that. Okay, and so let's go on, and we can use the completeness of the energy eigenstates to write this trace. So we can write this as a sum over m, and so this is the states that are going to define the trace. So let me move the a cubed sum over x out of this, and then we've got m whoops. I can also move the e to the I p dot x out here, and then we've got chi q x t chi twiddle q m. And then in the denominator, we've got a similar thing, sum over states, m e to the minus ht m. Okay, yeah, so as I said, the chi q's and chi q twiddles are composite operators built from the fields in the theory with quantum numbers q. And by translational invariance, I can actually take x naught and t naught and set these to 0. And then I can use the fact that operators defined at different times can be written, sorry, that the Heisenberg equations of motion for operators allow us to write operators at different times. So I can write, so we're going to use that operator at time t in Euclidean metric is either the ht operator at 0, either the minus ht. Okay. And so that allows us to make a spectral decomposition by inserting energy eigenstates at, between the operators. For example, we're going to insert an energy eigenstates here. Okay, so let's do that. So C2 of T and P is given now by a sum over the states M, a sum over another complete set of states N, A cubed X, e to the minus I P dot X. So then we have M, e to the minus H T, there's an e to the H little t, a e to the minus I P dot X, P hat dot X. So this is the momentum operator. We're also translating the operator at X here to 0. So we have chi hat Q at 0, e to the I P dot X, e to the minus H T, and then we have our state N chi Q twiddle dagger M divided by M e to the minus H T M. Okay. So now let's, for simplicity, we'll take the temporal extent of the space-time to infinity. And so you can see various things are going to happen. So here, we can act with the Hamiltonian on its eigenstate. So this is going to go like e to the minus EMT, right? I guess the whole thing's just the sum over m of e to the minus EMT. And similarly, these connect back here, this connect here, and so we get a e to the minus EM t minus t, e to the minus ENT, and the momentum operator can also act back on the eigenstate. That's such a good thing. And it's going to give us e to the minus I, the momentum of the state M dot X. And this one is going to give us e to the I Pn dot X. So these are no longer operators, they're the eigenvalues corresponding to these eigenstates. So let's write this out again. And we'll make use of the t goes to infinity limit, and then I will note that E0 is less than E1 is less than or equal to E2, and so on. And so in that limit, only the lowest energy state will survive in the sum in the denominator. And I'm going to set omega to be that m equals 0 energy eigenstate. So h on omega 0, and P on omega by translation and variance is also 0. Okay, so now what can we do? So looking first at the denominator, what's going to happen is that as t becomes large, only the lowest energy state is going to contribute. So this denominator is a sum over exponentials, but only one of them is going to survive. So it's just going to be 1 over e to the minus e0 t in the t goes to infinity limit. In the numerator, this exponential here, as t becomes large, is again going to force the energy, is going to choose the energy em to be the smallest one, so e0. So overall, there's going to be a factor of e to the minus e0 t minus little t in the numerator, which will cancel with that in the denominator. So let's write this out. So we have sum over n, a cubed sum over x. Let's write the phase here, e to the I, what is it? So it's p from the first term plus pm minus pn dot x here. There is e to the minus e0 This is divided by just e to the minus e m0. And we're free to set the ground state to 0. And so the denominator just becomes 1. And so this simplifies. And so now we have a sum over n, sum over x, e to the minus I, p minus pn. And yeah, by translations, p on the vacuum is 0. So the pm here is 0. E minus this, e to the minus en of pn t, and then we have, let's just write it as z n z twiddle dagger n. Oops, I didn't want those to be pink. Okay. And a couple of things to note. So this sum over n is really a sum over the energies and the momenta, right? So this is a sum over all eigenstates with energy En and momentum Pn. These Z factors come from these two factors here. So these are called overlap factors. And then finally, you can see that the only x dependence is in this sum here, and this is just a delta function. This forces Pn to be P. And so we get that this is sum over now En, because it's an A cube that I'm floating around. That's part of the delta function. So e to the minus En now of P T times Zn data. Okay. And so you see that indeed this correlation function is determined by the energy eigenvalues of the theory. So a couple of notes. If chi q equals chi q twiddle, so we have the same, or the emission conjugate operators, then Zn twiddle is Zn, and the sum above is um, is a sum over exponentials with uh, positive coefficients. Okay, the overlap factors. So Zn was omega IQ n really determine which states contribute in the calculation. Um, and while sum over n is a sum over all states, Zn is only non-zero if the operator chi q acting on the vacuum gives us something that has the same quantum numbers as state n. So for example, if our operator is something with the quantum numbers of the proton, then a single pion state does not contribute in this sum. Okay, so that's that derivation. Let me now just grab a question from down here. So I don't want to write it all out again. And leave this as an exercise to work on. So I want you instead to consider the 3-point correlation function defined here and derive how it also depends on the spectrum of the theory. And I want you to also ask what additional information is needed to describe this 3-point function, and what selection rules hold amongst the different quantum numbers q, q prime, and q double prime here, and amongst the momentum. Yeah, okay. And how would this differ if the correlation function was considered in momentum space? So I'm not doing, so if I didn't do this sums over x and y here. Okay. Let's do a little bit more and then take a break. So what do we actually know about this? So the sum over states is over an infinite tower of states. And so even in QCD, in lattice QCD defined at a given lattice spacing and volume, where there's a finite number of points, the Hilbert space is in fact infinite dimensional. Um, um, One way to see this is that QCD involves bosonic fields, and so you can have, just like the harmonic oscillator, you can have any number of excitations of those bosonic fields. And even on a computer, where we have a finite resolution in numbers in our floating point precision, the Hilbert space is very large. Um, when we do our lattice QCD calculations, what do we get is we get values of C2, P, and T at discrete T evaluated stochastically. And so given these two things, even if we have infinite statistics, it's an ill-posed problem to determine the En. We have a finite number of data points and an infinite number of E's that we need to determine. And while it is a unique problem if you have as many data points as you have energies to really invert this expression to get the ENs, in the case where you have more energies than data points, it's not doesn't work. Now, the stochastic uncertainty is a feature here. You only need to be able to describe C of T to better than the precision with which you know it, right? So if you have contributions from from high energy exponential contributions, if they're giving contributions that are smaller than your uncertainty on C of T, then they're kind of irrelevant. And so at a large time, only a finite number of states are going to contribute statistically resolvable contributions to this sum here. And of course, the number of states that that give that contribution depends on the overlap factors and on the precision. As you increase the precision, more states will be irrelevant. Okay. So one more question. Let me grab this guy. Cut. Paste. So this is an analytic calculation you can do. So let's take the case where the two operators are the conjugate of each other. And I want you to show that in uh, the large time behavior of C of t provides a rigorous upper bound on the lowest energy state with momentum p. Lowest energy state with the quantum numbers of chi q with momentum p. And you can assume that capital T is infinity, and you can work with infinite statistics. Okay, one last point here is real lattice calculations have a fixed T. And we impose, for example, periodic boundary conditions on bosonic fields and fermionic boundary conditions on, and antiperiodic boundary conditions on fermions. Um, and so you need to think about what we did up here, where we took the t goes to infinity limit, and that allowed us, for example, to neglect all of the states except m equals 0. If we don't take the t goes to infinity limit, then expressions become more complicated. So let's maybe just write out what happens. So C2 of P, T, and now capital T. If you go through the same logic, you can see that we can write this as a cubed sum over m and n sum over x e to the minus e m of q t minus t e to the minus e n of q plus p. Oh, sorry, this is a sum over q. Times some number z n m of q and p squared, right? Where this guy is m q chi q n p is the generalized version of the overlap factor. And you can see that this can get messy.